Hi, in this video, we want to take a look at importing and exporting spatial data. All right, so we're going to be following code from Applied Spatial Analysis with R. And so this is chapter 4, I believe. Here is the textbook's website, Applied Spatial Data Analysis with R-book.org. And this book is, you can download it for free if you're a UCF student through the library. Okay, so I'm just going to be going through the chapter code to just kind of explain specific points about it. I'm trying to emphasize in this video actually doing data analysis rather than theory or concepts. I want to, my goal primarily when I'm teaching and when I'm learning something is to be able to do it, then get deeper understanding second. And that's pretty much how I'm going to proceed with this. All right, so first thing that comes up in the author's code is that we get a data frame of different projection codes. So remember that when we're talking about maps, there's always a difference between the Earth and our representation with our map. There's always a distortion because we're taking the surface of a three-dimensional object and putting it onto a flat two-dimensional surface. All right, so that the distortion, the amount of distortion and the nature of it is determined by how we convert from three-dimensional object to two-dimensional surface. All right, and there's advantages and disadvantages for each individual projection depending on my project. So we have lots of different ways to go about this, lots of different options. Here, this data frame just tells us what are our options. And now, unfortunately, it doesn't tell us which ones are good and bad for particular projects, but at least it gives us information on what's available. Now, when we work with our projection, we can either enter a numeric code or we could give the projection arguments like this. Either way. Now, how do we get this? If I'm in the RGDAL package, I take the make EPSG, the European Petroleum Survey Group function. If I take this function, it will automatically create this data frame for me. And then I can see what's available and what's possible. Now, something that we can also do, if I want, I can also subset this just like any other data frame. So what I'm doing here is I'm grabbing only the rows where the note uses the word atlas somewhere. And now here, how I have it set up, it's capital A, then lowercase afterwards, atlas. And then I'm only looking at the first two columns. So I can treat this like any other data frame we have in R. Now, something that we always need to be mindful of is our coordinate reference system, which is our CRS. And this is from the SP package. Now, the keyword that we have for our parameter is the projection arguments. And these come from that data frame we just looked at a moment ago. And just this little bit of information tells R how to handle converting from the Earth to our map. Now, here are the specific features of it, of our projection. You can see that we've got latitude and longitude. We're working with a spherical structure. And here's which ellipsoid we're on. Remember that when we're dealing with our projection, most of the time we're approximating the Earth with a collection of ellipsoids. And plenty of stuff that if I need a more under the hood look at my projection, here it is for me to check out so that I can have full information of what's going on. And here's another one for our coordinate reference system. And something that's nice is when we see the area, when it's included, so we can know areas that this would work better for or worse for. Now here, what we're doing is I am getting the projection using the string that specifies it and putting that in to the CRS function down here. So that CRS function is to call the projection. This CRS projection call is to define what an object's projection is. You see how I have the arrow sign or the arrow operator going on. And we can see that the ed50 object now has this as its projection. Now, something we will also want to be able to do is if I have latitude and longitude, I would want to be able to convert that to degrees, minutes, seconds, or if I have degrees, minutes, seconds, to convert that to latitude and longitude. All right, so there's different ways to represent our location on the Earth. Latitude and longitude is probably the most common in modern practice, but there's still, something to be said for degrees, minutes, and seconds, especially if you like trigonometry. So what we're going to do here is if I have degrees, minutes, and seconds, and here it's referencing from Earth, from the east, and here's from north, I'm going to take the character to DMS and convert it over to a numeric, and that will give me the latitude and longitude. So I'll scroll down here. Yeah, here is the output for latitude and longitude. I should say longitude and latitude. And so once I have this converted over, so this is how I need to have it if I want it to be a character string. And then I use this and the as numeric function to convert it into actual numbers. And now I can go through and I can, so here I'm specifying what the projection is for this particular object. And I've got my longitude and latitude very nicely. Now, also, if I have longitude and latitude, I want to be able to convert to degrees, minutes, seconds. So to do that, we just take the DD2 DMS function and we convert it very easily. So here, I'm specifying that what I have is a coordinate. And then, and so notice that I'm treating things, I'm separating out, longitude and latitude here. That's important. But I take the numeric value, specify that's a coordinate, and then convert it over. And I'm going to save it as a character. Take the numeric object, specify that it's coordinates, convert it to degrees, minutes, seconds, and then save it as a character. And so now we can see that we've got the same values that we had a moment ago. So we can go back and forth. Now, the other thing that we might want to do when we're working in our spatial data analysis is know the straight distance between 2 points. Now, here, this will be distance between 2 points along the Earth. So if I'm talking about from like New York to Shanghai, the distance is not the straight line distance, which would be passing through the Earth. It's along the surface of the Earth. And so we'll call that the great circle distance between 2 points. All right. So to compute this, I just do spdis in one, and I just specify the points that I want. And here are the reference points. So I'm computing the distance from this point to all the points over here. There's only one, so it's not an issue. And I'm making sure that it knows what version of coordinates I've got, longitude and latitude. And if you remember the work I did previously, I set it up so that these are actually the same points on the Earth, from defining things as they were. So of course I'm going to get a distance of 0 because they're the same location. Now, this is the distance between points. If I want to know the direction, so let's say that I'm out in the woods, maybe I'm in the Army, I'm doing land navigation, I've got compass and I want to go from one point to another, and I want R to figure out my azimuth for me. Well, what I could do is I could use map tools, GZ azimuth. So azimuth is the direction that I will be walking in terms of a compass from one point to the next to go. And so here we've got our two locations. I need to, so in this format, they're numeric. So I need to specify them as coordinates. And then I pass those to GZ azimuth. And now something that's important is, remember, I need to specify my to and my from. So if I get backwards, I'm going to be pointed 180 degrees. Now, these are the same point on the ground because of the work we did previously. So I get an A because there, I'm already there. It's not, there's nothing up with it. Now let's take a look at what happens if, let's say, I didn't use the same projection. I've got multiple objects going on in my project. I'm doing my spatial data analysis, but I forget to make sure I have the same projection every single time. What will happen? Okay, well, let's go ahead and just say that this IJ Ed 50 has this projection, the 4230 projection. Now let's go ahead and make this with SP transform to have the WGS84 projection. Now I have same location, but different projections. Okay, so what's going on is I have the same place on the Earth, but I'm saying I map it to the flat two-dimensional plane map in two different ways. What's going to happen? Well, let's go ahead and compute the distance between my 2 points. All right. Well, we know that they're the same point, but yet I have positive distance. So something got messed up. Something's wrong. So this says that they are, this calculation says that they are different points, but we know that they're in fact the same. And if I want to compute an azimuth, if I want to go from here to there, they're the same point, so I shouldn't get an azimuth, but I see it's a -132. So this is saying that we would be going southwest. Yeah, you would want to, if you're using a compass, you'd want to convert that to 0 to 360 instead of having a negative value. Yeah, 360 minus 134 will give it to you. All right, so let's go ahead and list some tag information. All right, so the RGDAL projection info function, what this does is if I'm interested in a particular projection, I can see some of the description about some features. Now, when it comes to the type, there are 4 types that this function will work with. It will work with projections, ellipses, datums, and units. And so here, if I do the projection, here's the name, and here's a quick description of what's going on. If I'm interested in the ellipsoid, then I've got name, major axis, ELL, and then a quick description of it. And just like any other data frame, I can do all the data frame operations I'm accustomed to. So if there's a particular projection that a particular ellipsoid I'm interested in, then I can grab let's say I know the major information, I can use my data frame operations to grab the specific one I want, so I don't have to go scrolling through the entire data frame. Now for units, we can see like what units are typical, what's going on. And so here we have the ID, we have the conversion to meters, and then we have the name. Now there are 4 possible types in this. So here, including datum, and you'll notice that I did not present anything on datum because it wouldn't run on my machine. I couldn't figure out what was going on. All right, now this part of the code is very similar to what we did previously of converting a character to data degrees, minutes, seconds class object. So here I'm taking a character, and I'm converting the character to degrees, minutes, seconds. Now, something that's important is if I want to actually do this in real life and start building this up, I need to pay attention to the D and the slash, this special character and this special character to be able to do this. So this specifies degrees, minutes, and seconds. Now, when I'm talking about a degree, minute, seconds object, we have several slots. So the get slot functions, the function in R is a base R function that goes through and just tells you what are the items that we have, the storage slots in our object. And so we can see that we have a WS that's logical, degree, which is numeric, minutes, which is numeric, seconds, which is numeric, and north south, which is logical. And if I need to, I can always convert it to latitude and longitude by converting it to numeric very easily. Now, in RGDAL, there's the OGR drivers function that shows what we have available to work with as we're which drivers are available. Now, some of them will be like written ability but may not. I believe all of them are readable, but you're gonna have to work with each individual one, case by case. Things will have like different properties in terms of like write, copy, and is vector. So here are our different drivers. All right, so now let's go ahead and start working with some data. Let's actually get a map going, because we're doing spatial data analysis. We need to be doing maps. So what we're going to do is I'm going to read some data in. I'm using read.table to read in the Scotland.dat data sets, skipping one line. And then I'm going to specify the names of the data frame. To be district, observed, expected, PCF, latitude, longitude. Now this code won't run for me. Tried, wouldn't work. Now let's pull in some spatial data. So now I'm going to pull in a spatial polygons data frame using RGDAL read OGR. I'm only going to get the Scotland layer. And here I'm allowing loss, that if there's something to be lost, there's a problem, just go with it and proceed forward. Now you'll notice that when I look at that spatial polygons data frame, it does not have a projection yet. So using this function, I'm like, hey, what's my projection on this? Oh, I don't have one. I need to deal with that. So what I'm going to do here is I'm going to specify that the projection is going to be the WGS 84 projection. That's a good default projection. And I'm using the CRS function. All right, so now let's just take a look at what we've got. Let's check out our data. So here, how the author chose to do this was to grab the individual slots of the object of the spatial polygons data frame and just look at their class. So here, when I look at the data, we can see that we have a name and we have an ID for each row of our data frame. Okay, and so here are our IDs. Now, something that's going on is that we have two things, two objects for Scotland. We have a data frame, and then we have a spatial polygons data frame. I'm going to need to match them up. Well, fortunately, the IDs are in here. in the spatial polygons data frame, we have an ID column for the ID variable, while in the Scotland data frame,